Hi everyone, and welcome to our overview and demo of the CodeHawk Binary Patcher. The CodeHawk Binary Patcher enables high-assurance binary patching without a reverse engineer. My name is Michael Gordon, and I'm a principal investigator at Aarno Labs. Just quickly, Aarno Labs is an R&D firm, a spin-off of MIT, specializing in solving difficult problems in computer security, DARPA hard problems. We have experts in formal methods, dynamic analysis, malware analysis, and programming languages. And we build tools for transition into the operational environment that solve difficult problems, again, for the DoD mostly. So as for a little bit about myself, I have my PhD from MIT in computer science, where my research focused on programming languages, compilers, static analysis. And for the last 10 years, I've worked on research projects funded by the DoD and DARPA, building tools to do many things. For example, vetting untrusted applications statically, monitoring information flow and running applications, seeking and destroying botnets, binary patching, as you'll hear about today, runtime application security. And I've produced many open source tools used in vulnerability analysis communities like academic communities, DoD communities. And I'm really excited to talk to you today about CodeHawk. And let's meet the rest of the team.
Hi, I'm Henny Sipma. I'm the principal developer of the CodeHawk analysis system. My background is in theoretical computer science, and for the past 25 years, I've been building tools that put that theory, especially the absolutely awesome theory of abstract interpretation, into practice in the service of principled program analysis of both source code and binary code.
Hi, my name is Ben Carroll. I'm responsible for the patching component of the CodeHawk Binary Patcher. I earned my doctoral degree from the University of Pennsylvania studying garbage collection. My technical interests include the design and implementation of programming languages and related areas like type systems, static analysis, security, and compiler optimizations.
Hey, my name is Ricardo Barato. I am in charge of all the user interface and integration between the different parts of the CodeHawk binary patching system. I did my PhD at Columbia University. Back then I was doing remote display systems. And then I've done a number of different things, virtualization, applied neuroscience, and now I'm in doing programming languages and also caring a lot about applying those things to actual users. Thank you.
So now that you know the team, let's focus on the problem we're trying to solve. Long service legacy code is everywhere. Vehicles, heavy machinery, integrated control systems, medical devices, and lots of legacy code is end of life, meaning the original manufacturer no longer services it. And of course, end of life code has issues. Everything has issues. Security vulnerabilities, functionality bugs, requirements mismatches. And these issues are very hard to debug and understand. The original code, the build system might be missing. They're talking about stripped binaries. You don't have emulators or debuggers for a lot of end-of-life code. And so it's very costly to maintain end-of-life code when you find problems. You might have a long process with the original supplier if they're even willing to talk to you about their end-of-life code. That supplier might be out of business. The supplier might not have access to the original code or build process if it's something really old. And then if they do make changes or if someone else makes changes, it's really costly to retest, recertify, redeploy modified end-of-life code. So in today's solution, if you want to make changes without the original manufacturer, one possible solution is binary patching, where a reverse engineer, this magical beast, makes hopefully small changes to a binary. I mean, how hard can it be to make changes directly on a binary? Well, binary patching is extremely difficult and extremely costly. It depends on the skills of reverse engineers, which are rare. They're human, they make errors, and binary analysis, especially for patching, is an underserved market. There's a lack of formal and trusted analysis platforms. There are binary lifting platforms, but they're focused on the problem of lifting to understandable code and without trust of that lifting. There's a lack of analysis that's focused on understanding the changes of a patch when you make changes to a binary. And really, the question is, can the modifications be trusted not to break the functionality that you want to keep and to actually fix the problems that you want to fix? And right now, you have to rely on human review of machine code. Maybe you can test if you have access to a few tests, but really unverified tooling in terms of the binary analysis, and then relying on human review of the machine code to try to build trust and assurance in the binary patch. So that's the situation we're here to change. The CodeHawk Binary Patcher is drastically reducing the cost and increasing the assurance of third-party binary patching. And all this is done with formal methods. We're talking about static analysis of binaries. And this is all to enable third parties to be able to modify binaries, end-of-life binaries, stripped binaries, with high assurance and much lower cost. So this work was developed by Aarno Labs under DARPA's Assured Micropatching Program, or AMP. The goal of AMP is to create capabilities for rapid patching of legacy end-of-life binaries and mission-critical systems. AMP aims to create new capabilities to analyze, modify, and fix legacy software in the binary form without source code and with high assurance. And all this is focused on fixing security flaws in existing binaries. So first I want to motivate why we are focused on micropatching. So we loosely define a micropatch as a patch that modifies about 10 lines of code or fewer. So fixing vulnerabilities in end-of-life devices is hugely important, and studies demonstrate that the vast majority of security patches are small. 91% of security patches modify 10 lines or fewer. And our goal with our work with the CodeHawk Binary Patcher is to support sets of micropatches per update, because we see that 98% of security patches modify 10 functions or fewer. So these patches are focused and small. That enables us to build precise analyses that reason about the differences between the original and the patch binary. With micropatch-based updates, the problem then becomes, how do we assure the changes? This is a very hard problem because the patching party is not the original manufacturer, and we have to assume that we do not have the manufacturer's testing environment. So our goal is to enable the assurance of a patch given these assumptions, and we break down assurance into 3 sub-goals. We call it do no harm to the patient is the first one. Really, this means do not change desired behaviors. Number 2 is fix the underlying bug or vulnerability. And number 3 is prove the trustworthiness of the evidence. And we also call this meta assurance. So we mentioned the current status quo is ad hoc manual processes based on unverified tools. So our innovations developed under the AMP program, they changed the situation. So first we've created formal and rigorously defined specifications of a patch. So we have a human-guided workflow, that's the one we're focused on today, where we enable a user to directly modify C code to express the changes, where the C language has a formal specification, one in which we've encoded our analysis, and we have these great analyses that work on C code, as you'll see. And we also are, although we won't cover it today, we also support the definition of templates that find candidates automatically for transformation. These are like insecure coding practices, and then we can patch those insecure coding practices automatically to close a vulnerability. Our second innovation is, instead of having a human directly change the binary instructions, we've developed technology that applies the changes from the formal spec, meaning the change on the C code, to the binary. So it makes the changes to the binary automatically. So the developer doesn't need to be a reverse engineer to make changes to a stripped binary anymore. So our tool creates the changes to the instructions automatically and does other modifications required for some patches, like creating free space for ELF binaries and adding required hooks for trampolines. This gets us 2 things. So our tool makes much smaller changes to the binary versus human interventions. So like in the AMP program, we demonstrated there are patches were 99% smaller than human patches that using existing tooling, where functions are replaced or where functions are completely recompiled. And a small change set is great for precise change analysis, as we'll talk about. Our tools have a set of transformations that analyses can later validate, which we'll talk about. And 3, we designed and have prototype implementations for trustworthy analysis and the assurance products that we produce. So this is work in progress, but a lot of the foundational work has been done. So we currently support the production of understandable and intuitive assurance results. Precision is important in keeping the results tractable and understandable for a non-PhD in computer science. And we focus on the trust of our analysis with the goal of having each transformation or analysis step verified or validated. So now we want to give you just a high-level understanding of our processes. We have papers that talk about our underlying analyses. And if you want more information, you can always reach out to us. So the foundation we built our results on is required to be trusted, so verified or validated when we're working in kind of these high assurance environments like medical devices or industrial control systems. So we've developed the underlying binary and source analysis over the last 15 years. And in AMP, the DARPA AMP program, we developed a plan to verify or validate important steps of the analysis. And we put in place many steps of that plan. So the end goal here is to have complete trust in the analysis results. And the analysis results are invariants or facts about the binary or the C code. So just to take a step back, we talk about verified versus validated. So by verified, I mean, you can think of using mathematical proofs or formal methods to rigorously demonstrate that software behaves correctly in all situations according to its specifications. This process uses verification systems or tools. And by validation, I mean automatically checking artifacts against an independent validation system that checks a particular artifact. This demonstrates that that particular artifact output can be trusted. So here we see on this slide, like the early stages of our analysis pipeline are to be verified, and the final output, the invariants, can be validated. They're difficult to produce, but very easy to check with a checker. And just so you're clear what invariants are, they're facts about a program at a particular program point. These are calculated without running the program at static analysis, and they hold for all executions. An example could be like on a binary inside of a loop, we can pick out an induction variable, the analysis can, and it can tell us what values that induction variable takes on. In this case, like 0 through 10. And that's all. We can show that that's a validated fact about this code. And we can use that to we can use the invariants to build up more complicated proofs about program behavior, some of which we'll talk about later. Okay, so using our trusted analysis, our baseline analysis, we can produce a trusted lifting of a binary into a high-level language, in our case C. And as far as we know, we're the only tool that's working towards this level of trust for binary lifting. The lifting we produce then is editable. So we have provenance that links the expressions of the lifting back down to the binary instructions, and then has a bunch of other analysis results that allow our patcher, which we'll talk about later, to kind of make very efficient changes to a binary. So this process where you can directly edit C code, it removes the need for the human to understand the details of the binary. So now a typical C developer, as you'll see in our demo, instead of a reverse engineer, can express a binary patch. So once a human makes the necessary changes, we have as an artifact a well-defined representation of the semantics of the patch. This is source code. It can fit into existing processes for understanding the changes between source code, maybe existing regulatory or testing processes for verifying source code. And we can use our existing source analysis tools to demonstrate properties of the patch, which you'll see that we do. So now we have automated tooling that applies the changes defined by the source modifications on the underlying patch. This is the CodeHawk Patcher, we call it the patch application step. So our tool uses a rigorous definition of the C language to understand what is changed. So it compares the modifications to the original. So coupled with the analysis facts that we have about the original binary, that tool can then make minimally invasive changes to the binary to enact the semantics of the change that was made on the C code. So the patcher itself is unverified, but the output is validated, as you'll see. So now, since we have the specifications of the semantics of the patch, which is the modified lifting shown here on the left, which the human made, we can compare that to the lifting of the automatically modified patched binary on the right. So it's a bit subtle, but on the right side is really an artifact produced automatically by our tool. And on the left side really defines the semantics of the patch, really the modifications of the C lifting. So if they're equal, it's very strong evidence that the patcher tool that we created applied the semantics of the patch correctly to the binary. And we're going to show that in our demo, that we have a user interface workflow for looking at this and validating this. So what I've shown so far answers that question about the trustworthiness of the artifacts, the analysis, and the changes to the binary. So now we can use the invariants to demonstrate what has changed and what hasn't changed from the patch. So the binary invariants are used to build reasoned arguments about patched behavior. They're built from understanding the differences between invariants, and we've demonstrated in AMP that this is good for things like how behavior reconverges after a patch, how a patch affects a particular maybe state machine or protocol that we have a high-level model for. And the important aspect here is that very few changes are made to the invariants because of our minimally invasive patches that are produced by our automated patcher. And it's easy to comprehend and build principled arguments about those invariant changes. And this answered the question, does the patch affect any desired behaviors? That is, thinking about medical devices, does it do no harm to the patient? And finally, we can use the liftings we produce for the original binary on top here and the modified binary on the bottom, coupled with our semantic model of C code, to demonstrate how the patch changes high-level behaviors. For example, we can prove that a patch fixes a buffer overflow. And we use our C semantic model, which looks at the invariance of the original, the invariance of the modified C code, to prove that the patch fixed, let's say, a memory overflow vulnerability. And in this way, we could use invariants to prove adherence to other models, like protocols, if those models exist. Okay, so in the end, what we have built is a portfolio of processes and products, artifacts, that combine to provide high assurance of a patch. We have the verification and validation of the analyses and the transformations. We have the high-level specification of the patch in C code. We have the validations of the patch implementation versus a high-level specification. We have proof that a vulnerability is closed for important vulnerability classes that deal with undefined behaviors in C. And then we can build invariant-based proofs of changes to the behaviors, which we've done for various protocols and state machines over the AMP program. And then we have processes. We have human editing and review of the high-level lifting, which is the patch representation. And we have a human certification of invariance on the change of the patch, which we'll go through in our demo a bit. So the secret weapon here is the CodeHawk Binary Analyzer. So all of our work in AMP is built on top of CodeHawk, which is an open source industrial strength sound static analysis tool that has been around for about 15 years, and Aarno Labs is leading the development now of CodeHawk, the CodeHawk tool. And it's been proven over many IARPA and DARPA programs to do important things like solve important problems like malware analysis, vulnerability discovery, binary analysis as we're using here. It's able to recover source level constructs from binaries. We're talking about local variables, structure formats, function signatures, and discover these precise facts, these invariants, as they relate to source level constructs, which is really important for our lifting. It has now lifting, patching, vulnerability discovery, relational analysis, all these tools that we've built on top of it, and it has support for x86, MIPS, ARM32, and in process Power 32. So the CodeHawk Binary Patcher, the binary patching workflows are being developed in Binary Ninja as a Binary Ninja plugin. The analysis system for patching workflows is built on top of CodeHawk. And as I mentioned, CodeHawk is open source. All the Binary Patcher UI plugin code will be open source. And the CodeHawk analysis system is available to be installed locally. We can provide a container for it to run it locally, or soon we're going to provide it as a cloud service on the Binary Ninja Cloud. Okay, and now for the demo. So in the demo, we'll perform an end-to-end patch of a real-world security vulnerability in an industrial control system for an electric grid, which is another sector where high assurance is paramount. So this binary and problem to be fixed that was created by the evaluation team for AMP, an independent third party that builds problems that the AMP program needs to solve. These are challenge problems. And it represents a real world stripped binary with a real world security vulnerability. So we'll demonstrate our binary patching workflow where the semantics of the change are enacted by the changes of our lifting. We'll show how the CodeHawk C analysis demonstrates that the changes the binary fix, they fix the actual underlying memory overflow vulnerability. We'll prove that. And then we'll review our analysis, the lifting validations, the patch assurance artifacts, and we'll show the whole end-to-end pipeline. So now over to Ricardo.
Thank you, Michael. This is a demonstration of CodeHawk's binary micropatching system. The purpose of this system is to enable system developers to create binary micropatches on legacy software using high-level constructs and to be given assurances that the problem that they set out to address has been fixed. So I'm going to walk you through the flow that a system developer would go through when addressing, in this case, a buffer overflow vulnerability. So here we are in Binary Ninja, binary analysis platform similar to Ghidra and IDAPRO. And we start at the point where the developer has analyzed the binary within Binary Ninja and understands the problem that they need to fix, and they're ready to develop the patch. So first things first, you select the function that you're interested in, and then you navigate to our patch function plugin entry. So at this point, we've taken the binary from Binary Ninja, submitted it to CodeHawk, along with the information about the function that we're interested in patching. And then we're also giving it a number of information extracted from Binary Ninja, such as any annotations that the user has done on the code, and a little bit of other information. CodeHawk takes this particular binary and the function information, and then first it performs a very high-level analysis of the binary, and then it kind of zooms in on the function of interest and any code that is associated with that. Then once the analysis has been finished, it generates a very high-level lifting that I can show you here. So as you can see, there's the function that we were interested in fixing. The code looks very much like C. You have high-level types, you have global variable declarations, you have function calls. These are all functions that are being called by the target function. So in this particular case, the bug that we're trying to address is a buffer overflow at this line. Buffer position can grow beyond the bounds of input buffer and cause overwrite and potential security vulnerability. So the first thing that the developer is able to do is take this lifting and give it to CodeHawk's C analyzer. So what the C analyzer does is it has an understanding of C semantics and undefined behavior. It looks at the code, it analyzes it, and then it creates proof obligations. And then it reports when it's unable to discharge any of those obligations. So what that means for the point of view of the developer in this case is that CodeHawk is unable to prove that buffer position is never going to go past, it's never going to grow larger than 18, which, as you can see here, is the size of the input buffer, right? So in that case, you have an issue where, as I mentioned before, the buffer position can go past the end of the buffer and create a problem. So I'm gonna type in I'm gonna copy paste the patch. It's a little bit more complicated than I would like to just type from memory, and then I'm gonna kind of explain what's going on. So the way you develop a patch is that you just write C code. So as you can see here, you can reference these variables. So variables, for example, these are global variables. Declare here. You can make function calls. And so what this patch is doing is saying, okay, if the buffer position is larger or equal to 18, which is the size of our target input buffer, then we want to reset that. And then the additional functionality we want to do is we want to call a couple of functions that make sure that there's no pending data in the USB bus. So things to note here is that you're able to create very high-level constructs. Like you use very high-level constructs, you can make function calls, you can have loops, you can have empty returns, So very much an environment tailored towards system developers. Right? You don't have to be an experienced reverse engineer to develop a patch. Okay, so we developed this patch. Let's see what the analyzer thinks about it, see if our issues have been addressed. And most of them have gone, right? So we can see that our possible patch is here, but we still have one issue. And what this is saying is that CodeHawk is unable to prove that buffer position will not be negative, right? So then you would end up with a buffer underflow. And the reason for that is that buffer position has been declared as a signed integer. So in this kind of scenario where you're dealing with a global variable, it is really hard to prove that this is the only function that modifies its value, right? Because if we look at the code, we can see that this, buffer position can never be negative within this function, right? But because it's a global variable, we have no idea that, another function could be modifying it. So we're going to implement a very conservative patch where we're going to say, well, if the buffer position turns out to ever be negative when it comes in here, we really don't want a buffer underflow, and so we do the same process. So now we once again analyze the lifting, and now we don't get any more red boxes, which means the analyzer believes that the code as written here addresses any particular issues that are with this function. So, we're pretty happy with this. It seems like we're going on a right patch. So now the next step is to click here and say generate patch. We get an error, and this is expected because depending on the kind of else binary that you're dealing with, we have some heuristics that are able to automatically create space for the patch. And I'll mention in a moment why we need to create space. But in this particular binary, it's strange enough, let's call it, that our heuristics don't work. And so we need to ask the user to please tell us where we can find free space. The most straightforward way to do that is to understand that there's a particular function that has not been, it's not used, or at least in the scenario that you're interested in, and then mark it within Binary Ninja. So let's do that. Okay, so we're going to navigate. And I know this function is not used because this particular program was given to us as a challenge problem as part of our evaluation for some of the work we're doing for micropatching. I think I forgot to mention that this was developed as part of DARPA's AMP, which is assured micropatching. And so the evaluation team gave us this particular challenge problem, and then they sort of tell us that this particular routine is not used. So we can use it. So you find it there, and then you, with Binary Ninja, you tag it. You tell it, okay, this is the range. This is the address range that we are allowed to use to implement the patch. So we do that, we mark it, and then we try again. Okay, and everything worked. So this was a very straightforward process for a patch, and what's going on under the hood is that we sort of automated the more tedious and error-prone parts of binary patching, which is figuring out the code that needs to be inserted, figuring out the kind of where to put it, where in the binary it should go, creating a trampoline for it. The reason we need a trampoline in this case is because we're inserting code, right? So if we were just to put the new code where the existing function is, then we would move everything, and then a large part of the binary would change, which is something we want to prevent, and I will talk a little bit more in a moment. So in this case, the patcher was able to generate the trampoline, the patcher, everything worked, and then we get a sort of details of what's going on. So we were told that the way we implement trampolines is a very straightforward process where we have a payload that implements the actual logic, so the code that we put in there, and then a wrapper that's able to mediate between the original code and where that logic is. And then we're providing with more details. So the next step, now that we have our patch binary, is to analyze that patch binary. This is where CodeHawk shines at giving the developer very high-level assurances and understandable assurances that the patch has been implemented correctly and that the patch addresses the problem they are interested in solving. So let's submit the binary again for analysis. And so once again, we've submitted the patch binary to CodeHawk. CodeHawk is analyzing it, figuring out where the differences in the binary are using some of the information that the patcher has generated and provided, and then doing some very deep analysis that compares the two parts of the binary that change. So once this is done, we get this splash screen or summary screen. And the purpose of this screen is sort of to give the developer first high-level assurance that the system did what they expected it to do, right? So, and that it, in particular, that it changed as little of the binary as possible. So as we can see here, we're told how many the original binary had, in this case 525 functions, and the patch binary has 524. I'm going to explain in a little moment why that went down. And then out of those, 523 have completely unchanged, right? So right off the bat, you understand that your patch binary is almost the same as the original, right? And this is very important for legacy software. This is very important in cases where you need to do expensive recertification or testing. So if we go down here, then we're told exactly what changed in the binary. So let's start with this one, right? So this is loop, this is the function that we wanted to patch, and of course that would change. And then here is the function that we marked using tags, where the trampoline went. So that explains why in the patch binary there's one function, right? We took that function that was marked, and now it's being used for the trampoline. Down here we're presented with a number of lifting and patching validations that the system does on itself, right? And the idea here is that to assure and give some proof and create some trust in the developer that the system did what it was expected to do, right? So if any of these validations don't look right, then you know that there was something wrong that happened in the patch process. And there's also a chance that this would not, provide a successful result. It would more than likely result in an error. And then over here we replicate the parts that, the summary of what was changed in case the user is interested in looking deeper, right? So if you're a system developer that has some assembly experience, you could dig down and understand what the patch logic was at the binary level. But we're focused here on high-level assurance. So the next step we're going to do is we're going to do this high-level lifting analysis. And we've seen this before, but there's something very different here, right? So on the left, once again, is the original lifting that we extracted from the binary. And we have all those errors that the C analyzer flagged. And then on the right, we have the lifting that actually comes from the patch binary, right? So it's not what we submitted, so it's not the exact same analysis as we did before generating the patch. In this case, CodeHawk has analyzed the patch binary, it has lifted it, and now you're submitting that into the C analyzer. And so as we can see, here's the line that we were interested in fixing, and there are no issues. And then, key to notice is that up here, we have the logic, which looks a little bit different from what we submitted, and we'll address that in a moment. But so here's the logic from the trampoline, and as you can see, CodeHawk is able to validate that the trampoline structure that was put in place is correct, and then is able to analyze through it and inline all that logic that's in the trampoline and put it as part of the main lifting, right? So now you get a complete unit that can be presented to the C analyzer, right? So we have a binary analyzer and a C analyzer, and they're completely separate. So the binary analyzer is creating a lifting in C that represents what's in the binary, but in a way that is easy for the C analyzer to consume and understand that the logic is part of the function, and it can see it and say, okay, yes, the logic that you have in that trampoline has completely addressed the problem that you set out to fix. So that's a very good assurance that the trampoline was implemented correctly, and that the trampoline logic that we put in place actually addresses the vulnerability that we wanted to address, right? So we no longer have a buffer overflow or a buffer underflow. So next up, we're going to do a comparison of the lifting, right? So on the left-hand side, we have the lifting that was extracted from the original binary. on the right-hand side, we have the binary, the lifting that was extracted from the patch binary. And so, once again, we see that code that was part of the trampoline. But then something really important to notice here is that a large part of the function is completely unchanged, right? So we're not only trying to say, okay, you modify this function, we're going to recompile the whole thing and put it in place. We're actually being very surgical, very specific about the instructions that we change, because you can have very complicated functions and you don't want to modify them completely, because then your assurances get really complicated and your recertification and your testing can get really complicated. Instead, based on using CodeHawk's analysis of the binary, we're able to precisely understand where in the binary, and which instructions need to be changed to implement the patch, to implement the trampoline, and we only modify those instructions specifically. Right? And then we're going to do a comparison of what you submitted, you as a developer, to the system and what was actually implemented, right? So this gives you an idea of how the code that you wanted to implement was actually put in place, right? And again, remember that what's on the right-hand side, this part over here, that's this ground truth that's coming straight from the binary. Right? So we can see that my original patch was very succinct, but if you look at this code on the right, we can see that the logic is there, right? And so the key here is that the developer doesn't have to worry about the details of what's going on in the binary, like the details as in like the specific machine instructions, how how things jump, like a while loop, how it's implemented in the binary. Instead, they can focus on, okay, this is exactly what's in the binary. Does that actually reflect what I wanted to implement in my patch? So we're lowering the effort and allowing the developers to focus their effort on the high-level details that are important when generating binary patches for legacy software, right? This is software that you may not understand 100%, that somebody may not know, there may not be all source code available, any number of challenges, and we don't want to add the challenge of having to understand things at the binary level. Instead, we're lifting it to a friendly environment, a known environment where it's C code that you can reason about in a high level. So we have another assurance analysis result that gets you a little bit lower level and under the hood, in case that's something that you want. So in this case, we're comparing the control flow graphs for the original function, which is on the left-hand side, and then the patch function that's on the right-hand side, right? So I'm going to zoom out a little so you can sort of see that the structure is quite different. But as we'll see as we zoom in, the structure is only different for a single basic block. So we have this in first basic block. And if you remember, when my patch, I put the patch right at the top of the function, so it's expected that that's the one that changed, right? So here we highlight that the first instruction on that basic block didn't change, and then here's where we jump out and start all our trampoline logic. So we have the trampoline setup block, then we have the payload. So here's that while loop that drains the USB bus, and once that's done, then we get into the case of whether we decide, do we do an early return or do we go back to the original logic? And here we can see that we highlighted this instruction that was part of the original block, so that's still there. So we perform that now, and that's part of the trampoline code, right? So that's the instruction that we overrode in order to insert the jump to the trampoline. And now we fall back to the original code. We have this instruction that is here. And then if we go back down here, we look and we see that all this code is completely unchanged, right? So as I mentioned before, we're doing very surgical changes to the binary. And so all this logic, which includes sort of, a number of basic blocks that can be implemented in very complicated logic, have not been changed in any way. So in some sense, you can sort of not have to worry about them. And you can go even lower and look at the binary level differences for the binary if you want to just get all the details or you just want to understand what's going on. right? So we give you some very high level assurances, but you can go deep down into the details and investigate as much as you want whether the patch was implemented correctly and it does what you need it to. As a final note is that this whole process is kind of built on this idea of iteration, right? We don't expect patch developers to implement a patch right the first time or for everything to work first time. So if you come to this part of the process and something doesn't look right, then you can just simply say, try a different patch. And what this will do is will send you back to the patching screen, which then with the patch applied, and then you can either modify the patch or try a different one. And then once you're satisfied with the results and you're moving to the next step, then you can save the patch binary, and then you will get a binary that you can then go and do recertification, you can do more dynamic testing, and so on. Thank you so much.
Thank you for watching this video covering the CodeHawk Binary Patcher. If you have any questions, please reach out to us. We'd love to talk to you. Take care.